Hello, I'm Devendra Kapadia, manager of Calculus and Algebra at Wolfram, and this afternoon I'll speak about asymptotic computation, which is just a simple way of getting approximate formulae for several mathematical problems. Whether you are a mathematician or a computer scientist or a physicist, you will find this talk enjoyable and easy. I look forward to seeing you. Thank you. Okay, hello everyone. I'm Devendra Kapadia, and I'm the manager of Calculus and Algebra at Wolfram. And I'm speaking about a rather large project, a team project, which we've been working on for the last couple of years. That's on asymptotic computation. And I do appreciate you all showing up over here at 4 o'clock in the afternoon on the last day of a conference. I really do appreciate it. So thank you very much for being here. And well, that sounded like a really technical area, but in fact the goal of asymptotic computation is very simple. Given a problem, a function, a sequence, a differential equation, a difference equation, integral, whatever, find a simple approximate formula for that problem. And of course, when you have an approximate formula, then you lose something. What you lose is that you can't wander too far away from a point. That's where the word asymptotic comes from. So we'll work at a point, work close to it, get a nice formula, and that's it. And over the next 20 minutes or so, I'd like to give you a thorough introduction to what we've done. So I'm going to begin with Stirling's formula, which I think is where asymptotics really began in the 18th century, a very well-known formula, and then talk about the asymptotic function, which is the main new function, super function for version 12.1. And once I've got that set up, then we talk about integrals, integral transform, differential equations, and asymptotics for them. That's continuous calculus. When that's done, I'll switch gears and talk about discrete asymptotics of sequences using a discrete asymptotic function. So that's a new function. So you've got asymptotic for continuous, discrete asymptotic for sequences. And then once I've got that set up, I'll talk about how you can apply it to sums, products, summation, transform, and difference equations. And last but not the least, a vast area of asymptotics is the asymptotics of algebraic equations and transcendental equations. And I'll try and cover that as well. So that's the goal for this talk, to try and cover that area of asymptotic computation. So let's begin with Stirling's formula. So it's not universally well known, but what's now called Stirling's formula is actually due to Abraham de Moivre. So de Moivre was quite a fantastic mathematician, and in fact, he knew Isaac Newton, and Newton would often say that, go to de Moivre, he knows more about these things than I do. So, but de Moivre made his living by tutoring and gambling. And in 1730, he discovered a formula for approximating the factorial. It looked pretty good, but he was missing a constant somewhere. And that constant is square root of 2 pi, which you see over here. And a few months later, his friend James Stirling told him that that constant is square root of 2 pi, and that's what became Stirling's formula. So Stirling's formula was rediscovered by de Moivre. And the main point in asymptotics, he who nails the constant gets the fame. Okay, so we'll see today that these formulae really require you to know some constant. And but if I say over here asymptotic equivalent of x factorial is that Stirling formula, then all that means that the factorial has a ratio of 1 to that in the limit as you go to infinity. That's all that there is. So we have two new functions, asymptotic and discrete asymptotic, which compute the asymptotic approximation for functions, sequences, and operators in the most general sense. So that's the goal for this talk. So let's begin with asymptotic. So simple example, take the sine function, work near 0. We all know from high school almost that sine x is approximately equal to x as long as you're close to 0, and that's the linear approximation to sine. Now, you might want more terms. You say, I need more accuracy. Then you have got this option called series term goal for asymptotics, which you can say goes to 12 over here, and you get back a certain better approximation. And that approximation is pretty good, as you can see over here. So let me just go down, and just a minute. There you go. Okay, so that's a much nicer approximation. And in fact, I think that this kind of formula is a much better way of doing calculus. Now that I teach calculus quite a lot, it's a much nicer way of doing calculus than working with circles and trigonometric functions, because you can just differentiate over here and see that the derivative of sine x is cosine x, etc. So I think that the asymptotic viewpoint actually dominates all of calculus, although we don't know it, and we never call it that. Okay, so just to prove that point over here, I'm going to show you a gallery of function asymptotics. So I have a polynomial, a rational function, a trig function, the airy function, a trig function again, polynomial trig, and the prime pi function from number theory. So all these functions have got nice asymptotics. There you see. So in each case, the red curve is the actual function. The blue dotted curve is the asymptotic. So the first polynomial is asymptotic to 2x cubed. The second rational function is asymptotic to 1 over here, as you can see. And sine x is asymptotic to x, etc. So the point is that this kind of asymptotic approximation you do all the time when you do calculus, and it's really what drives the whole of calculus 1, for example. Okay, so once you understand what asymptotic is, the question is, why is it so important, and why did we give it this strange name, asymptotic? I had lots of almost objections. How can you call something asymptotic? Well, the reason is that we want asymptotic to be like n in Mathematica, where you do n of integrate, you get n integrate, do n of sum, you get n sum, do n of d solve, you get n d solve, etc. So now I can actually plunge into calculus. So here is an inactive integral, and if you don't know the secret of that, why it's inactive, just mouse over it. You see it's inactive integrate. I have disabled integrate. And this example actually is from a book on advanced calculus by Woods, which Feynman used to study calculus. So I took up that book. That's the example he probably studied, his famous trick of differentiating an integral sign. And I put it into asymptotic. And I said, find the asymptotic for me. And in about 0.2 seconds, it gave back the answer, exact answer. Now, of course, you could use asymptotic integrate for the same thing. But the main point is that in this case, this answer is not just approximate, it actually is exact. And the question is, why is it exact? Well, that's why asymptotic is good, because it gives you insights into why things are what they are. So what you see over here is if you do a series expansion, then that term, the 2 log a term, is the one that's actually doing all the work. The other terms are harmonics, and they just die out in no time at all. So all the cosine terms over here are harmonic, but over the interval 0 to pi, they all give you 0. So in fact, the asymptotic answer is the exact answer. Now, if you look at Woods, it takes 1.5 pages to give you the answer, and here we get back in 0.2 seconds with no work at all. I didn't know that in advance. So that's integrals. That's about half of calculus 1 done. Now on to integral transforms. So we got lots of integral transforms. We got Fourier transform, Laplace transform, Hankel transform, Mellin transform, Redon transform. Every 2 days, someone says, here's a new transform. Oleg wants a D transform. So we cannot keep on having asymptotic this, asymptotic that. So we need one super function into which you can throw what you like. It'll do the right thing. So over here, you have a function which is obviously has a Laplace transform. It's decaying very, very fast. So I throw it into asymptotic. Why the inactive? Well, I must disable it because it's going to take a long, long time, probably tell me that we cannot do the Laplace transform. And even with a single term over here, you actually get back a pretty good asymptotic approximation. So my point is that you will always be able to get good asymptotic approximations using the asymptotic method, as long as things are kind of reasonable over here. Okay, so I just need to find my mouse over here. Where am I? Okay, oh, sorry, it's lost. Okay, fine. Okay. Sorry, just a minute. I'll be back. Okay. So back to integral transforms. And so you see over here that actually have quite a nice answer with almost no effort. On the other hand, the difficult problem is how do you compute inverse Laplace transforms? Now that's a big area. We're just getting into it. But you see over here that we actually can get a very nice asymptotic inverse Laplace transform in many good cases. So you can do Fourier, inverse Fourier, Laplace, inverse Laplace, whatever you like, using the asymptotic function. Okay, so now on to differential equations. So here's a differential equation. Looks pretty simple, but there's an e raised to x in it. So that's a non-rational coefficient. It's impossible to solve that, at least as far as I know, with current functionality. So you see over here that if you divide by the x cube, you actually have a singularity at 0. So that's the complex plot showing that over here. And the main point is that that singularity actually is an irregular singularity. So it's not an ordinary point. It's not a regular singular point. It's an irregular singular point. But the same technique that works for rational functions also works for exponential functions and these singularities, and you get back a nice solution like you would in a course on differential equations at college level. So you can do asymptotics of lots of things over here, and you get back nice answers simply by using all these tricks of approximation. Okay, so now I can go on to the discrete side of things and discrete asymptotic. So begin simple with the Stirling formula. So the Stirling formula is just what you saw early on. It's e to the minus n, n to the n plus half times square root of 2 pi. But of course, you can go much further than that. So here's a nice table of things, of discrete asymptotics. I've done a lot to collect them. But if you're an expert in the area, I'm not an expert in this area really. If you work a lot of sequences, you know something, let me know. Okay, but on the left, you have a sequence, n factorial, Fibonacci, harmonic number, prime, zeta, binomial, Pochhammer, Euler, and partition P. And those on the right are the asymptotics for those sequences. So now we are into the sequence world, and you can do the same kind of trick that we've done early on for this. Sorry?
Where is prime type?
It's not, it's continuous. So prime is, that's the problem. Okay, here's the problem. We have got two worlds. You've got a continuous world, a discrete world. In the continuous world, you can be where you like in the complex plane. In the discrete world, you can go to infinity. If you're really ambitious, go to negative infinity, and you're done. In the continuous world, everyone loves continuous special functions. We got Oleg and other people, really experts. In the discrete world, things get really, really sparse, and people might spend a whole lifetime trying to get one more term of some number theory function. So I admit we are kind of limited over here. If you know what to do over here, let us know. Okay? But I think that's a nice table which shows how powerful these asymptotic formulae are. Okay, so now I can move on from there and having set it up, talk about sums and products. So for version 12.0, we have this new function called asymptotic sum, which does asymptotic sums. But then a long time ago, 2007 probably, I developed this so-called divergent series functionality. And I wrote a blog post called the ABCD of divergent series, which is surprisingly popular. Even today, I get emails like every few months saying, I like that blog post. So the question is, can we do asymptotics of divergent series? In a sense, that's the only place where you want to do asymptotics because you don't have a good convergence criterion at all. So over here, what you have is a divergent sum, pretty messy one. I'm saying Borel regularization, which is a kind of regularization, and you get back a nice, simple answer over here. If you didn't do that, you might get a Bessel function or something like that. But this answer is actually pretty good for most purposes. Huh?
So if you just did some of that with oral regularization, can you get an answer?
Yes, you get a Bessel answer.
Okay.
But the thing is that what we do is we cut into the implementation, frankly. And at the point where you're actually doing all the hard work of summing or integrating or whatever, we do the regularization kind of stuff. So in many cases, the two will agree, but there are examples where they will not. So this expands the whole thing out. And at the least, you get back a nice approximation compared to having Bessel K, which is a kind of pretty horrible function to work with. You get back this nice power kind of thing, or gamma actually in this case, yeah, power. Okay, so one new kid on the block for version 12.1 is asymptotic product. And you see it over here. This is actually based on a paper by Garrett Birkhoff. And it's a very nice example because the point is you can do the asymptotics, but it's almost impossible to determine the constant over here. So when you try and determine the constant over here, it's hard to get exactly. And you can see over here that the input is exact, but the output is inexact. And that's the new philosophy, that we're going to allow this kind of situation where we don't have a real good idea of what the constant is, but you can think of this approximation as being an approximation of a real constant. And the approximation is pretty good over here. Okay, so I don't know. So let me scroll down a little bit and show you. And you see the approximation is pretty good at even 80 terms. Okay, so now I go on beyond this and, yes, there is. So now all our symbolics functions from now on will have numerics options, working position, accuracy goal. Not that I know how to work with them, but yeah. Okay, I mean, so really we are trying to have one, instead of having two different functions, we'll have one function which allows you this freedom. So by default, we make a good choice. So we say working position goes to automatic, and we can do what we like, or you tell us and we'll do it for you. Okay? Right. But that's a good question, yeah. So, okay, so let me go on now to summation transforms. So, you know, when I did my PhD a long time ago, I took pride in not doing combinatorics. And when I was kind of depressed, I would tell myself, at least you don't do combinatorics for your PhD, you know? So for a long time, I had this kind of feeling that that's not an interesting subject. But last year, Roger Germundson, who's actually driving our project, showed me a wonderful book. It's called Analytic Combinatorics by Robert Sedgwick and Philippe Flageolet. It's only 700 pages long, and it's free on the web. So I started the book, and the idea is this, that you have a sequence, let's say. Then you find its generating function, let's say, by some method. But you don't know the sequence. And the generating function is like a clothesline on which you hang the sequence. And the pegs of that sequence, of that clothesline, are the powers of z over here in that expansion. So a generating function is what encodes all the information about a sequence, although you may not know sequence itself. So here's an example from their book. It's 1 over 2 minus e raised to z, and you work out a few terms. It looks pretty dreadful and absolutely hopeless. The fractions seem to grow quite a lot. But discrete asymptotic will do the following. It will go into the generating function, look at the singularities in the complex plane. Keep in mind you're working with the integers, but we do a singularity analysis, get the leading term, and you get back this really nice asymptotic for the sequence. And that asymptotic actually gives you back a wonderfully accurate answer. Okay, so the point over here is that you can always get nice answers by doing discrete asymptotic. Okay, let me push it down a little bit. And you see over here that the asymptotic is actually going to give you a pretty good approximation for the actual sequence. So I don't see the thing over here, maybe it's down. Okay, so that's generating functions, summation. So you can do Z transform, inverse Z transform, Fourier sequence transform, what do you like, with discrete asymptotic. Okay, so on to the next theme, which is differential equations. So there's a nice story behind this. So in 1960, actually, Andrei Kolmogorov, the famous Russian mathematician, organized a seminar. And this seminar had a purpose. The purpose was to show that school book multiplication, which you learn in high school, is the most optimal way of multiplying two numbers. And he's a big man, organized a seminar, and a week later, a student in that seminar, 23-year-old Anatoly Karasuba, told him he was wrong. And in fact, found what was one of the first divide and conquer algorithms for multiplication. And you would think that Kolmogorov was very annoyed with him. He did nothing of that sort. He said, he canceled the seminar, wrote a paper in Karasuba's name without letting him know, and publicized the work everywhere. So that's Karasuba multiplication, which I believe we have in Mathematica even now. Is that correct, Mark? Sorry? Yeah, so it's Tim Cook, and yeah, so multiplication kind of algorithm come by day. But the main point is that you save one multiplication out of 4 by doing Karasuba. So instead of 4 at every step, you have 3 multiplications. And that reduces the complexity from n square to n raised to power 1.58. And that was the great achievement of Karatsuba. And you can see over here that we get back this beautiful asymptotic formula for this rather wonderful approximation. And if you look at the graph below, you see that, in fact, we have a plot over here which shows the Karatsuba and the school book multiplication. So initially, school book seems to be better, but very quickly, Karatsuba takes a much smaller number of steps. Okay, so that's differential equations, and now on to algebra. So we have a very nice function called asymptotic solve, which can do both algebraic and transcendental equations. Now, this particular problem over here is the Kepler equation, and that's a famous problem. So you can do an approximation. You can see approximation is really good. And I could spend some more time on this, but my main point is that one good thing about our team, I'd say generally speaking about our department, is that we have pretty good documentation. So this example over here is more or less stolen from Itai's documentation of asymptotic solve. So these days, giving a talk is no problem at all. Go to documentation, copy, paste, and you're done. Okay, add some fluff to it, and you're okay. So I invite you to look at this wonderful page that Itai has written for asymptotic solve, and you will get lots of examples for transcendental equations, algebraic equations, etc. You know, algebraic geometry is an old subject, and every century they go up in dimension by 1. So in the 18th century, they had, I think, curves, then surfaces. Now they're threefold. So if you come back after 1 century to attend the conference over here, they'll be talking about fourfolds. So that's a vast area, but we are trying to capture it with asymptotics. But I think that what we have is really a nice mix of functionality for all kinds of asymptotics. So my main point is that we really want to drive this asymptotic computation to its very limit. And in doing so, I just want to make sure that we try and get into every barrier, then try and cross it as easily as possible. But that's about all I had to say. I'm really running out of time. But my main point is that this asymptotic computation is like a third mode of computing. In addition to you've got symbolic computation, numeric computation. But keep in mind, they have had 30 years, and the world's best developers, we've had 2 years. So please forgive us if you've got some things not working right yet. We will get them working soon. The second point is that going forward, we'll continue to develop continued fractions, etc. But for now, I think we have reached a very good stopping point. And I hope you think that this asymptotic computation really is the new mode of mathematical computing. So I'll stop over here. Thank you very much.